Welcome everyone to my first official Monday step-by-step tutorial, and we are starting with trigonometry. What is trigonometry? Well, make sure to stick to the end to find out and how to use SOH CAH TOA to find angles and sides in trigonometry. What is trigonometry? Well, it's basically just a form of measurement that allows us to find angles and sides in triangles, plus a lot more advanced stuff which we'll cover in future tutorials. Right, so the next few months, every Monday we'll be doing different trigonometry tutorials in order, right? So let's kick off. So with trigonometry, we're just going to start with right angle triangles. So in a right angle triangle, we have, in respect to one of the angles, which we call theta. So in respect to this angle theta, this side here next to it, we call the adjacent side. This side here that is opposite is named the opposite, which makes sense. And this side here is the hypotenuse, which is always true for a right angle triangle. So the only thing that changes is opposite and adjacent depending on where theta is. If theta is here, that's the adjacent. If theta is here, this will be the adjacent and that will be the opposite. So using this, we can now define the three trigonometry ratios. The first trigonometry ratio is sine theta, which we define to be the opposite over the hypotenuse. Right, so sine theta equals the opposite over the hypotenuse. This is why these are called trigonometry ratios, because this is a ratio between two sides. The next trigonometry ratio, cos theta equals adjacent over hypotenuse. Right, so the full name is cosine, but we just shorten it to cos theta. And the last, tan theta equals opposite over adjacent. Right, so this is shortened from tangent. Okay, so these are the three main trigonometry ratios we will use to find angles and sides in right angle triangles for now. There are other ratios, but they're introduced in later topics, right? More advanced topics. Okay. Now there is a great way to remember these trig ratios, and that is SOH CAH TOA. Right. So you see here, sine theta is opposite over hypotenuse. Look at this, sine opposite over hypotenuse. Cosine is adjacent over hypotenuse. Cos adjacent hypotenuse. And then tan is opposite over adjacent. Tan opposite adjacent. Right. So you can see this is a great acronym we can use to remember the three ratios. And eventually we won't need this acronym. We'll know all of them off by heart. But as we're starting out, the best acronym to remember, SOH CAH TOA. Okay. So let's look at how to find angles and sides in right angle triangles using SOH CAH TOA. Let's start with finding sides. So in trigonometry, we now deal with angles and sides in right angle triangles. With Pythagoras, you just dealt with the sides. Now we're introducing angles. So if we have an angle and a side, that means we can find any of the other sides we want. So we look here, we want to find x, we have 5 and 40. So step 1, identify which sides you're given in relation to the angle you're given. So that's in terms of opposite, adjacent and hypotenuse. So this can either be a mental process, or as we're starting it, we can actually write it on the diagram, which I recommend if you're beginning. So this is a given angle, right? So in relation, this is the adjacent side, this is the opposite side, and then this is the hypotenuse. So by writing that on the triangle there, it's going to really help you as you're starting out on how to find missing sides and angles. Step 2, use SOH CAH TOA to write down an equation for the unknown. So at this point, we're trying to find x, so now we need to write down the appropriate trig ratio to find x. So when I'm starting out in the question, you're not going to be given SOH CAH TOA, so write it down. So in an exam, I see this question, I've labeled the sides, I'm going to write down SOH CAH TOA. So we look, I'm given opposite and hypotenuse. Which one is that? That's sine theta. So straight away, using the definition sine equals opposite over hypotenuse, I can write sine 40 degrees, because that's the angle we're given, equals x, because that's the opposite, over 5, because that's the hypotenuse. Step 3, solve the equation for the unknown. So you see at this step, this is an equation to solve for x, because sine 40 degrees actually just represents a number, right? All these trig ratios just represent some kind of number, right? Because these are trig ratios, and ratio just compares two sides, so obviously that's a ratio. Now to solve this, we go back to equations. Now there is a trick if x is in the denominator, so simply all you have to do, I'll write down a simple trick here, show you what that means. So here, to solve this, I'm running out of space, we've got space here. All I have to do is multiply, and what it means is multiply this number here, because we want to get x by itself, so that means I need to get rid of this number here. Since it's dividing, we'll just times it over. So x equals 5 sine 40 degrees. Now note, when you're timesing numbers over with trig ratios, place the number in front of the trig ratio. It's very confusing to put it after the 40 degrees because you might think it's a part of the degrees. So always put the number in front of the trig ratio. Now to find out what this is, we need our calculator. So comment below, but I probably should do a future tutorial on how to use a calculator and trig values properly. But for now, we just put 5 and then you find the sign button on the calculator and just type in 40, close your brackets, which I'll do a future tutorial on to show you how to use a calculator. And I'm going to put my answer to 2 decimal place, 3.21. Okay. So let's look at another example where we talk about x is in the denominator and what I mean by swap. So let's look at this example. So x is here, 25 degrees there, 4. So step 1, let's identify what sides we're given. So 25 here, this is the adjacent, that's the opposite, and that's the hypotenuse. So then we're going to use step 2, SOH CAH TOA. So I'm given adjacent and hypotenuse in respect to this angle, that's cos theta. So cos 25 degrees will equal the adjacent, which is 4, over x, which is hypotenuse. So step 3, solve the equation. Now x isn't in the denominator. So a great trick to find x straight away is all you need to do is swap x with the angle. So that means x equals 4 over cos 25 degrees, because they will swap positions. Because when we're solving equations, I'd have to move x over here and then move the number back over here by dividing. So I would times x over, divide cos over, which just results in swapping their positions. And now we use the calculator to solve. So we just put 4 over cos 25, close the brackets, and we'll use 2 decimal places again. Alright, so that's pretty much how you find sides in a right angled triangle using trig if x is in the denominator or numerator. So let's look at how to find angles. So finding angles. Now the good thing about finding angles is it's the exact same process of finding sides. The only difference is how we solve the equation. So step 1, identify the sides. So this is in respect to this angle we're trying to find. This is the opposite side, this is the adjacent, and this is the hypotenuse. Let's write down SOH CAH TOA. So we have opposite 3, adjacent 7, that's tan theta. So then tan of theta, because we don't know what theta is, we're trying to find theta, equals 3 over 7. That's step 2 done. Step 3, solve the equation. Now here's what you got to understand. Tan theta is not a multiplication, so I'll just write that here. Tan theta does not equal tan times theta. Right? Tan theta is a ratio. It's tan of the angle theta. So to solve this, we're going to use the shift tan button on the calculator. So what that will look like is it'll be theta equals tan inverse 3 on 7. So this is not a power, this is the inverse button. This is the shift tan. So on your calculator, you'll see above the tan button, which I'll do a future tutorial on just how to do this properly, but there's a tan to the -1. So what that means is tan inverse. So what it allows you to do is find the angle from the ratio. So on the calculator, we press Shift, tan, then in the brackets, we will put the fraction 3/7, close the brackets, equals. And we get 23.20 degrees. So for now, I'm going to leave it as 0.20 degrees because in the future tutorial, I'll talk about how to use minutes, right? If you want to use the minutes, we're going to use this button on the calculator, that button, because that button on the calculator turns degrees, minutes, and seconds. So if I press that, I get this. I get 23 degrees, 11 minutes, and 54.93 seconds. So most questions will ask you to round to the nearest minute. So I'm going to do a full tutorial on how to deal with the calculator and rounding degrees. Okay. So that's it for this tutorial on how to use SOH CAH TOA to find sides and angles in a trig. Right, this is just an introduction tutorial on how trig works and to find missing sides and angles. So make sure to tune in next week when we deal with probably more advanced trig problems with right angle triangles or the calculator tutorial. Hey everyone, today I'm going to show you a really neat trick on how to remember the exact value ratios for trig just using your left hand, right? Forget about drawing triangles or using a calculator. We're just going to use our left hand and make sure you stick to the end to see how we find the values for sine, cos and tan. All right, let's start. So when you're taught how to remember the exact trig value ratios, they teach you to draw these triangles. All right, 60 degree, 30 degree, root 3, 1, 2, 1, 1, 45, 45, root 5, and then we get all these 6 different values, or 9, right? 6 here, so sine 30 is a half, and etc. You can see these are the exact values we're talking about. And there's also, but this trick I'm going to show you also works for 0 and 90 degrees, right? So these triangles only give you 30, 45, and 60, but my trick will also help you get 0 and 90 degrees. So is this what we're going to do? No, we're just going to forget about this method, right? And I'm going to show you how the trick works. Okay, everyone? So here's how this trick's going to work. We're going to get our left hand, palm facing us, right? So this is my thumb. So this is the thumb, and this is the pinky finger. And then we're going to sign, the thumb is 0 degrees. The index is 30, middle is 45, ring is 60, and pinky is 90 degrees. So those are the fixed angles for each of those fingers. So all you need to know now for sine, cos, and tan are what are the exact numbers. You don't need to know what angle goes with which side, you just need to know the exact side. So these ratios. So for sine and cos, the 5 exact values for these 5 angles are 0, half, root 3, 1 and root 2, and 1. They're the 5 different values. So how are we going to remember those just using our hand? Well, the trick for sine is we're going to list in increasing order. So what is the order these start from lowest to highest? Well, and how would you work it out? Well, here's the order. It's 0, then it goes a half, 1 on root 2, root 3 on 2, and 1. That's in order from smallest to largest. But how would you remember which goes where? Well, to know how to compare these numbers is if we square them, right? If we square a half, we get a quarter. We square 1 on root 2, we get a half. If we square root 3 on 2, we're going to get 3 over 4. So obviously you can see a quarter, half, 3/4, that's increasing order. So what that means is we have these values right here with our left hand in increasing order. So 0 degrees is 0 for sine. So sine of 0 is 0. Then we go here, sine of 30, what's the next value? A half. Then sine 45, what's the value after that? 1 on root 2. Sine 60, what's the value after 1 on root 2? That's root 3 on 2. And sine 90, what's the highest value? 1. So with this trick, you can just count on your hand. So I go here, all right. So in the middle, sine 45, what's the order? It goes 0, half, 1 on root 2. There we go. Sine 45 is 1 on root 2. So now let's look, how does this work for cos? So for cos, it's the opposite. List in decreasing order. So now 0 degrees is 1. 30 degrees is root 3 on 2. 45 degrees is still 1 on root 2 because cos and sine are both the same there, and there's a reason for that. That's the complementary identity. Then what's 60? That's a half. Lastly, what's 90? 0. So the key to remember here is to remember each value of each finger is 0, 30, 45, 60, 90. That stays the same. Then you just need to know what are the 5 values in 0, half, root 3, 1 on root 2, and 1. And then sine is increasing order, and then cos is in decreasing order. So with practice, you'll be able to just use your hand to count what it is without having to draw a triangle, and you'll be able to do it pretty instantly. And then cos go in reverse. So let's lastly look at tan. So for tan, what are the exact values? Well, we've got 0, root 3, 1, 1 on root 3, and undefined, right? Because by definition, tan 90 is undefined because cos 90 is 0. And we'll talk about that in a future tutorial on tan's relation to sine and cos, if you don't know it already. So then what's the trick for tan? The same as sine, increasing order. So the increasing order for this one is really straightforward. 0, 1 on root 3, 1, root 3, because 1's in the middle. 1 on root 3 has to obviously be less than 1 because root 3 is bigger than 1. Because square root of 1 is 1, so anything bigger than square root 1 will have to be bigger than 1. So that's how we go for tan. Tan 0, 0. Tan 30, what's the next value after the 0? That's 1 on root 3. Tan 45, what's after that? 1. Tan 60, what's after that? Root 3. And then tan 90 is undefined. So that's the trick to using your hand to remember, your left hand, how to remember the sine, cos, and tan exact values for 0 degrees, 30 degrees, 45, 60, and 90. They're the main 5 you need to know, because using those 5 you can work out pretty much all the other values in different quadrants, which is for a future video. Okay, so if you enjoy this trick, I recommend to start practicing it, right? Because it's really neat once you get the hang of it. Instead of having to draw a triangle, just use your hands. You'll be able to associate the exact values with each finger. And sine, remember, increasing order from thumb to pinky, cos decreasing order, so pinky to thumb, and tan is the same as sine, it's increasing order. Alright, so if you enjoyed this little trick on how to remember the exact values, let's get into it. First question. So the first question comes from Grace. So you'll see the question in the bottom here. There are 2 triangles, each with a hypotenuse reaching up and stopping at the top of a building on the right. You have to find the height of the building. The large triangle reaches further to the left, and the angle of elevation with the ground is 28 degrees. The small triangle has an angle of 40 degrees. Okay, so if we draw a diagram, we've got a tower here, or a building. We don't know the height, so I'm going to call it X. Then we've got a small triangle. So remember, these are not every triangles with angle of elevation 28 degrees. No, sorry, 40 degrees, sorry, that's the smaller one it said. And then the larger triangle, which is further to the left, so further to the left, has an angle of elevation 28 degrees. And then it says the difference between these grounds is 275.59 meters. You don't know the distance to the bottom of the building, so you have to find that. So pretty much the question looks like we're going to find the height of the tower, and all we're given is the distance between the 2 points here and the angle of elevation, right? So the key here, in order to find X, would be to find this side or the whole side. Now, and that way we can use basic trig. So if we dissect the problem, the only information we're given is this side here between here and here. Alright, so we're going to have to use this triangle to find this length y, because what we can do here, since this is 40 degrees, using basic geometry, this angle is 140 degrees, right? They're supplementary angles. So what I've got now, I've got 2 angles in this triangle, one side and one unknown side. That means I can use the sine rule. But remember to use the sine rule, right, is A on sine A equals B on sine B. So if we're starting with this side y, which is the unknown, the opposite angle is 28 degrees, and then the known side is 275.59, and its angle is this one up here, which we don't have yet. But I've got two angles in this triangle, 28, 148. So straight away, by angle sum of a triangle, it's 12 degrees, right? All three angles have to add up to 180. So straight away, I can plug this in. So y goes with 28 degrees, 275.59 goes with 12 degrees. Right, and now we just solve for y, and all I will have to do is, it's dividing here, so to move it up here, I times it over. Okay. And at this stage, you just get your pocket calculator out and plug that in. Right, 275.59 sine 28 over sine 12. So we'll use two decimal places like the question's done. 9. And now it's the hard part of the question over. Because now I've got y, look at this, this is a basic 90-degree triangle. I've got this angle, I want to find that side. I have that side. So look at the ratio. If we go to SOH CAH TOA, that's the opposite side, that's the hypotenuse, so that's sine. So sine 40 equals x over y, which is, we found this here. So to find x, again we just times this over because it's dividing. So 622.9 sine 40. Again, get your trusty pocket calculator out and we'll put it in two decimal places. Well, what do you know? Exactly 400.00 meters. That seems nice. Alright. Grace, hopefully this helps, and let's go to the next. So the first question is find the 5 remaining trig function values for theta given that cos theta equals negative 2 root 3 on 5 and cosec theta is greater than 0. Okay. Alright, so when we're dealing with this, this is part of the topic, find the value of a trig ratio given another. So first off, we need to know what quadrant we're in. Okay. So cos is negative. What quadrants is cos negative in? Well, if you do your all stations to central acronym, is what we learn here in Australia, all stations to central, cos is negative in quadrant 2 and 3. Okay. Now cosec theta. What's cosec? Well, cosec is 1 over sine theta. So where is sine theta? Positive. If we look here, it's just 1 and 2. So then we look, where's the overlap? Well, the overlap is 2. So we're in quadrant 2. So that tells us if our answers are going to be positive or negative. Now to find the values, we go to here and we draw a right angled triangle for theta. So we ignore the minus because the minus just tells us what quadrant we're dealing with. So cos theta is adjacent over hypotenuse. So this is 2 root 3, and this is 5. Okay, so now we need to find the opposite side. So we use Pythagoras, which would be square root 5 squared, so 25 minus 2 root 3 squared, which is 12. Right? 2 squared 4, root 3 squared is 3. So that turns into minus root 13, or just root 13. So now we can just list down the other ratios. So sine theta. So sine would be root 13 over 5, and we're in quadrant 2, so sine's positive. Then we can write down tan theta. Opposite over adjacent, root 13 over 2 root 3. That's shocking. 3. Now we're in quadrant 2. Tan is negative, so we're going to chuck the negative there. So now we need the values of the other 3, the reciprocal ratios. So the first one would be cosec theta, which is 1 over sine. We use the third letter to remember that, which I'll do a future video on. So that means we flip this. So it'll just be 5 over root 13. Then sec theta is 1 over cos theta. So we're just going to flip that. 5 over 2 root 3, and we'll leave the minus at the front. And lastly, cot theta. We're just going to flip tan theta, right? Because cot is 1 over tan. So 2 root 3 over root 13 with a minus. So whoever posted this question, I hope this helps. And for anyone who struggles with these type of questions, I hope this helps. Let's get. Welcome to another Monday step-by-step tutorial. Today we continue the trigonometry series with how to solve 3D trig problems step by step. So if you have trouble with 3D trig problems, then make sure to stick to the end to see how it's done. Alright, so what are 3D trig problems? Well, it's trigonometry in 3 dimensions. So what's step 1? So draw a diagram of the 3D problem, right? And then this is important. So this is if the diagram is not given. But you've got to make sure to label each point, all the given values, your unknowns which you're going to have to find, and compass directions. Right? Because these are going to make step 2 a lot easier, which is, so draw each relevant triangle, so the 2D version, from your diagram in step 1. And relevant means it has given info or unknown values you need to find. So this is the trick for 3D trig. 3D trig problems are tricky and very hard to visualize. So what you do once you have your diagram, if they don't give it to you, is convert it to a 2D problem, because 2D problems are much easier to solve. So then what's step 3? So step 3, find the triangle that links all the diagrams from step 2 and use either basic trig, sine or cos rule to put all given and unknowns you can into that diagram. Because you'll have a few 2D triangles in here, but in order to answer the question, there's only going to be one triangle, main triangle, that we're going to use to answer the question to find the unknowns. So this is why it's important to label each point, because if you label each point, you'll be able to see which triangles link properly, which sides and angles go together. And then it's just a combination of basic trig like your SOH CAH TOA or the sine and cos rule. They're the only things we've got to find sides and angles. Okay, so then that leads us to step 4. So again, what happens now is, because we've got one main triangle to work with, all our unknowns and given info is in that diagram, we're just going to either use basic trig, sine or cos rule to find those unknown values. Because everything's in that one diagram, we've got our angles, our sides. So if it's a right angled triangle, we can use basic trig. If it's a non-right angled triangle, we'll use sine or cos rule. And that's pretty much it. So then the last step we've got to do is write the answer in terms of the question. So you're going to get a value for your unknowns in here, but you're going to have to put that in terms of what the question's asking for. Okay, is it the height? Is it a bearing? So just some notes about bearings here. So when we have bearings, every north line is parallel to each other, right? Because the direction north is parallel to itself. So that means if we have multiple north lines, we can use our alternate angles, corresponding angles, or co-interior angles from geometry. So as you see, pretty much trigonometry is a combination of geometry as well. Right, so don't forget, we're going to need to use basic geometry to help us. So look at this trick, the board's clean. Alright, now that the board's clean, let's apply that step-by-step procedure for an example that covers pretty much most kinds of 3D trig problem. Alright, so I've got the question here, you should be able to see in the corner here. The diagram shows two observers P and Q 600 meters apart on level ground. The angles of elevation of the top of T of a landmark TL from P to Q are 9 and 12 degrees respectively. Alright, let's just draw a diagram. There's a diagram they gave us, right? Cool magic trick here. So now, step 1. So they're giving us the basic diagram, which really helps, but now we're going to label all the given info on that diagram. And they've labeled every point for us, which is very helpful. So they've told us P and Q are 600 meters apart. The angles of elevation are 9 degrees and 12 degrees respectively from P and Q. So this is 9 degrees here, 12 degrees here. And then they said the bearings of the landmark from P and Q are 32 degrees and 306 degrees. So if we include that, we need a north line at P and a north line at Q. And the bearing is along the ground. So L is on the ground, P to L. The bearing is this angle here, which they said was 32 degrees. And then the bearing from Q to L, which is along ground here, which is this angle here, is 306 degrees. So if this complete angle is 306 degrees, that means what's left here is 54 degrees to get to 360 degrees. And then they've said, let h be the height of the landmark. So that's our unknown. Okay. So let's see everything. So find the angle PLQ. All right, don't need that anymore. So then we can go to step 2. What's step 2? Is draw each relevant 2D triangle. And we've got 3 here. We've got the base, which I'll put here. P, Q. Then don't forget we've got these north lines that it looks so north. 54 degrees and north here. 32 degrees, that's 600, and that's L. So that's that base diagram. Then we've got these 2 triangles here with the angles of elevation. So 9 degrees P, T, L, and then the other one, L, 12 degrees. Don't forget H is here, H is there, Q, T. So that's step 2 done. We've taken every main 2D triangle from that question that has given info or unknowns. So now we're ready to start step 3, but first, what we can do now is part 1 of the question shows show that this angle PLQ is 86 degrees. So in order to do that, we need to use these bearings. So this is that note I made at the end about bearings. North lines are parallel to each other. So what I can do here is create another north line. That's another north line. So all these north lines are parallel to each other. So since we're trying to find the angle in here, you'll notice now that all these lines are parallel to each other, which means I can use alternate angles, corresponding or co-interior angles. And we can see here that this is a Z shape, so that is alternate angles. Straight away they're 32, and then straight away this is 54 degrees. So in total, you get 86 degrees for angle PLQ. Okay, so just make a note, by alternate angles, since north lines are parallel, we get 32, 54, which adds to 86. So that takes care of the first part. Then the next part of the question, just have a quick look. What is the size of angle BA? No, sorry, wrong question. Find expressions for PL and QL in terms of H. And why is that important? Because this is what step 3 talks about. This base diagram here relates everything, right? Because PL comes from this triangle, LQ comes from this triangle, and then this triangle has 600 and an angle. So this is the one triangle that relates everything. So now we need to use basic trig to put all the unknowns and given values onto this triangle, which is these 2 sides. So you can see here, using basic trig, tan 9 degrees equals H over PL. So that means PL is going to be, if we swap it, H over tan 9. And then we can just write, therefore, QL will be H over tan 12, because it's the exact same process except I swap 9 degrees for 12 degrees. So those are the 2 values for PL and QL, which we put onto this diagram here to complete step 3. Right, so at the end of step 3, you should have one diagram that has all sides and angles given in terms of the given info and unknowns, which we've got all these 3 sides and an angle in terms of given values and unknown values H. So in step 4, so this was step 3, step 4 is now we need to use sine, cos rule or basic trig to solve for the unknown, which is H. So look at this, is a non-right angle triangle because we're only given 86 degrees. So that means straight away sine or cos rule. So the trick with sine or cos rule is just look at what you're given. I've got 3 sides and an angle. So what formula relates that? That is the cos rule, right? Only the cos rule, which is c squared equals a squared plus b squared minus 2ab cos c, has 3 sides we can plug in and an angle. Sine rule can't do that. So then if we plug it in with c being the side opposite the angle, you get 600 squared equals h squared on tan squared 9 plus h squared on tan squared and 12 minus 2h squared cos 86 over tan 9 tan 12, just by timesing these sides together with cos 86. And now this is an equation where we need to solve for h. And the question says show h is approximately 79 meters. So what you'll notice is each of these has a h squared, which means I can factorize that out. Tan squared 9 plus 1 on tan squared 12 minus 2 cos 86 on tan 9 tan 12. That equals 600 squared, which means I can rearrange and square root. By dividing this over and square rooting, we get h equals 600 over, this looks fun, doesn't it? 1 on tan squared 9 plus 1 on tan squared 12 minus 2 cos 86 on tan 9 tan 12. Right? And the reason we leave it as 1 on tan squared 9 instead of changing it to cot is because the calculator does not have cot. So this is actually how you're going to have to type it into the calculator. Right? So now, where's the answer? This thing was working before. So we can see we got the answer there, 78.88. The question said showed equals approximately 79. Well, that just equals 79 meters if we round it up. Okay, so that's basically how 3D trig problems are solved, step by step. Most problems are broken down like this and either use sine or cos rule at the end here, if it's a non-right angled triangle. Don't forget basic geometry helps, such as Pythagoras and normal parallel lines. So that concludes this Monday step-by-step tutorial. Okay, so the first question. Given sine pi on 10 equals square root 5 minus 1 on 4, find sec pi on 5 in the form a root 5 plus b. And a and b are real numbers. So if you haven't done radians, I'll just make a note. Pi equals 180 degrees. So that means this is 18 degrees, this is 36 degrees. But we don't really need that. You didn't even really need to know what pi is, because you can notice, all right, so I'm told sine pi on 10 equals that. I want to find sec pi on 5. So you got to think, what's the relation between pi on 10 and pi on 5? Well, you can see that this is twice that. So 2 times pi on 10 equals pi on 5. And then we want to find sec pi on 5. So that means we are going to need a double angle formula to do that. Which one do we need? Well, sec, you should realize, is 1 over cos. So we need the cos double angle identity. So we're going to need the cos 2 theta. Now, which cos one do we want? Well, we know what the value of sine is. So that means we want the cos 2 angle theta formula that involves sine. There's 3 of them, but only one that has sine by itself, which is that one. So if I use this formula, sub theta as pi on 10, that means cos pi on 5 equals 1 minus 2 sine squared pi on 5. So now, all I need to do is sub in sine pi on, whoops, sorry, that's 10. I need to sub in sine pi on 10. So let's do that. Now I need to square that. So I can do that straight away. So to square this, we square top and bottom individually. So to square the top, that's going to be a perfect square. We square the first term, 5. Double their product, minus 2 root 5. Plus the last term squared, 1 over, what's 4 squared? 16. Let's simplify that. Now in one go, 6, 2, 8, all right. 3 minus root 5 on 4. What I do here, I cancel this 2 with the 16, that takes it down to 8. I added the 1, that's 6. And then there's a factor of 2 that cancels at the bottom. So now let's just put all that as one fraction. So then that's 4 minus 3 plus root 5 over 4. So notice when we combine into one fraction, we're adding a whole number with a fraction. So I did make a tutorial on that the other week, adding whole numbers with fractions instantly. You just times the denominator with the number and add it to the top. And this minus affects both of these. So that's why this is a plus here. So that's just 1 plus root 5 on 4. So then sec pi on 5 is the reciprocal, which means we flip it. Actually, I want to write with root 5 first. Now if we look at the answer, it says put in the form a root 5 plus b. We have a root on the bottom, so we're going to need to rationalize the denominator by timesing top and bottom by the opposite sign. So on top, that's 4 root 5 minus 4. On the bottom, that's difference of 2 squares, 5 minus 1, which is 4. And what you'll notice is this 4 will cancel if each of these falls on top, so we're left with root 5 minus 1. It's a very simple, nice looking answer now. Okay, so whoever's question this was, I hope this helps and you see how to do this nice and easy. All right, let's get to the next one. Okay, so the next question. All right, so we've got general solution here. So I've written down the example I'm going to do. All right, there's a lot there, so I'm just going to show you 2 different ways as a bonus of how to solve this using general solution. And then it says to find the values of theta in the domain negative pi to pi. So the first way we deal with trig equations is we try to solve them by reducing it by factorizing. So we want to sub in the double angle identity here, 2 sine theta cos theta, bring the cos theta over. That way we can factorize it out and solve it that way. So if I take cos theta out, that's 2 sine theta minus 1 equals 0. Then this turns into cos theta equals 0, sine theta equals a half. So now I have to find the general solution for each of these. So the general solution formula for cos theta equals A is theta equals 2n pi plus minus cos inverse A, where 2 pi, remember, is 360 degrees. So then cos inverse 0 is just pi on 2, right? Because cos pi on 2 is 0. Now sine. So if sine theta equals A, the general solution is n pi plus negative 1 n sine inverse A. Now there are 2 different formulas if we split n into even and odd cases, but why learn 2 formulas when you can just learn 1? So this is a better formula to learn. It covers all cases. So then sine inverse a half is pi on 6, right? 30 degrees. So now to solve in the domain negative pi between pi, we just have to sub different values for n in. So let's start with the most basic one, 0. So if we put 0, we're going to get plus or minus pi on 2 here, which is inside. So that's good. If we put it here, we're just going to get pi on 6. That's in there as well. Let's try the next one, 1. Now if we put in 1, 2 pi plus pi on 2 is too big. 2 pi minus pi on 2, still too big. That's 3 pi on 2, that's still outside. Let's put it in here. So it'll be pi minus pi on 6, 5 pi on 6, that is inside. So you can see now if I go to n equals 2, it'll be way too big. So we go down, and so let's check negative 1 then, right? Because we can sub negative values in because we've got a negative domain. If I put negative 1, negative 2 pi plus 2 pi, still outside, right? That's negative 3 pi on 2, which is still out here. Negative 2 pi minus pi on 2, way too negative. Okay, let's check here. Negative pi minus pi on 6. What's outside? So there is no solutions here. So then these are the final 4 values of theta, and that's how we solve using general solution. So now let's look at the bonus method of another way to solve this. So when we're solving general solution, or trig equations in general, we only want one trig value. So what I could have done here, instead of using a double angle identity, is I could have converted this to cos pi on 2 minus 2 theta equals cos theta. See, I use the complementary identity, right? The 90 minus theta. And the reason I changed sine to cos is because that general solution looks a little nicer than the sine one, so negative 1 to the power of n. So now if I apply the general solution formula, this is pi on 2 minus 2 theta equals 2n pi plus or minus theta, because cos the inverse of cos theta will just give you back theta. And I picked to put this one first because it would look better to have this here than that with a plus or minus. So what happens now is this is actually two different equations with the plus and the minus. So I have to split it into two equations, plus theta and then minus theta. And then I have to rearrange and make theta the subject. So here I would bring it over here. So I get 3 theta equals pi on 2 minus 2 and pi, just by swapping these. And then in one go I can write theta equals pi minus 4 and pi over 6. Let's do the same over here. I take it over here. If we swap it, we get theta equals pi on 2 minus 2 and pi. Or if I want, I can write it as pi minus 4 and pi over 2. So again, that's just different ways to write theta, and then to get the values you just sub in n again. Alright, so I hope this makes dealing with general solution a little easier. The key is just to remember the general solution formulas. Like if you know those formulas, then it's not too hard to apply it, and then to solve it in specific domains, you just sub different n values in. Alright guys, that's it for episode 4. So make sure to join the free Maths Help group. Link will be in the description. Hey guys, and welcome to another Tuesday trick, where today we'll be looking at cos double angle identities and picking the right one, right? So there's 3 different cos double angle identities, which makes it quite tricky when knowing which to pick. So when it comes to trig proofs, there is a simple trick. So let's kick off. So there are 3 cos double angle identities, and what are they? Whoa, how did I get there? I'm just a math magician these days. Okay, so the key is, when we have trig proofs, how do we know which one to pick? Well, in order to understand which one to pick, we need to understand what are the purpose of identities. And the purpose is to simplify the problem. Right, so when we have a proof, we want to use identities to simplify the problem. Now in maths, what's one way to simplify the problem? Well, it's reduce the number of terms. So we can reduce the number of terms in a problem. That makes life a whole lot easier for us. So that's the trick we're going to use here. We want to use the cos double angle identity that reduces the number of terms. So how can you recognize that trick? Okay, look at this. 1 plus cos 2 theta equals 2 cos squared. 1 minus cos 2 theta equals 2 sine squared. That's just by rearranging this. So if you have a double angle in the question for cos, and then you've got a plus 1 next to it, that means we use this identity because the 1 will cancel with the minus 1. And then same with here, we've got a minus. So that minus will cancel with that one. So the aim is, for the trick with the cos double angle identity is pick the cos double angle identity that will eliminate the 1, which is either going to be one of these two. This identity is rarely ever used in trig proofs. It has other uses in other places, but in trig proofs, it's usually going to be one of these two because we want to eliminate the 1 in there. So, whiteboard's clean. And let's look at an example now of how to apply this trick. Let's consider this example. Prove 1 plus cos 2 theta plus sine 2 theta over 1 minus cos 2 theta plus sine 2 theta equals cot theta. So clearly here, we can see we've got double angles everywhere, and we've got this 1 plus 1 minus. So what we're going to do is we'll start with the left hand side, And straight away we know the trick is we want to sub, for 1 plus we sub in the 2 cos squared identity because that cancels the 1, so that just turns into 2 cos squared theta. Now what's sine 2 theta? Well, luckily sine 2 theta double angle identity, there's only one option to pick from, which is plus 2 sine theta cos theta over. Now we've got 1 minus cos 2 theta. So which one cancels the 1? Well, that's the sine squared identity, and you should know 1 minus cos 2 theta is just 2 sine squared theta, and again, sine 2 theta only has one option. So from this point, to help us, I did a tutorial a couple of weeks ago on the manipulation list for trig proofs, which I'll leave a link up to here. So the manipulation list is E, F, A/S, S. So at this point, what's my next step? Do I need another identity? Well, let's go through the list. Do I have anything to expand? No expansions. Factorize, yes. Right, lots of common factors here. So we can factorize by taking 2 cos theta out, and we're left here. And then on the bottom we can take 2 sine theta out, and we're left with sine theta plus cos theta. And then look at this, they cancel. The 2's cancel. I'm left with cos theta over sine theta. We're trying to prove that equals cot theta. Go down the list, that means we need another identity, but that is just cot theta by definition, which equals the right hand side. So you can see, by knowing this trick with the cos double angle identity, it makes solving these proofs really easy. So the key is to know which one it is, and it's the one that eliminates the 1. Sine double angle is just 2 sine theta cos theta, so there's no problem with sine 2 theta, it's just the cos double angle identities. So I hope you enjoyed this tutorial, and I'll see you tomorrow. Hey everyone, in today's Thursday trick, we're going to look at how to solve trigonometric identities using T formula. So make sure to stick to the end to see what are the T formula and how we can use them to solve trigonometric identities much easier, and a trick. So what are the T formula? Well, it's based on letting t equal tan x on 2. And if we do that, then we get different identities for sine, cos, and tan x. So sine x is 2t on 1 plus t squared. Cos x is 1 minus t squared on 1 plus t squared. And tan x equals 2t on 1 minus t squared. These are derived from using the double angle identities, because we're x on 2x. So those are double angle identities. So leave a comment below if you want to see on how to prove these results, where they come from. So I'll do that in a different video. If you want it, just make sure to comment below. But here's the interesting thing with T formula. As I said, it's to do with double angles. So look what happens if I do this. So instead, if I let t equal tan x, what happens? Well, now the double angle result will be sine 2x, cos 2x, tan 2x, and you know what happens? They have the same values. So that's the beauty of this T formula. Doesn't matter what you do, as long as it's a double angle result, x, 2x, x on 2x, sine, cos, and tan will have the same values, which is very important. Right, so in questions that involve 2x, you're not going to use t equals 10x on 2, because that would be a 4 angle. We don't have a 4 angle result, so we only have double angle. So your substitution would be t equals 10x. So now let's do 2 different examples of how you would apply these and why these proofs are much easier, and a trick to make them much easier. So let's look at this example. Prove cos theta plus sine theta minus 1 over cos theta minus sine theta plus 1 equals tan theta on 2. So we can use these T results when the question involves double angles only. Because here we got theta on 2, here we got theta. That's a double angle. As soon as you have different angles, such as like theta or phi, you can't use it. Or if you have a 4, like this is theta on 2, this is 2 theta, I wouldn't use it. Right, so T results or T formula work really well when we have a double angle. They're much quicker than using ordinary trig results, because people find these proofs quite tricky. Okay, because using normal trig identities confuses people. But what happens with T formula is we're going to reduce it down to an algebra proof. And algebra is much easier to deal with than trig. So we start with the left hand side. And now because we have theta on 2 and theta, our substitution is t equals tan theta on 2, which means we don't have to write it, we can just sub it in. If we're using t equals tan theta on 2, that means cos theta is 1 minus t squared on 1 plus t squared, plus sine theta is 2t on 1 plus t squared, minus 1 all over, pretty much the exact same thing. Okay, alright. Now here's a nice trick to make this even easier. Right, because now we've gotten rid of all the trig, it's only algebra left. So here's a trick, and I'll leave a link. This is an example of a compound fraction. So I did a quick tutorial a few weeks ago on how to deal with compound fractions. I'll leave a link here to see it. So the trick to get rid of compound fractions in one step is to times top and bottom by the LCD. And if you notice here, 1 plus t squared is the LCD here and here. So if I times top and bottom by 1 plus t squared, the fractions are gone. So this will cancel that fraction. I'm left with 1 minus t squared plus 2t. Now then I have to times this term as well because we're timesing this with every term. So it'll be minus 1 times that, which turns into minus 1 minus t squared, right? Because it's minus 1 times each term over. Again, this is going to cancel with that. And now, so that's minus 2t. And now it's plus 1 times that. So it's plus 1 plus t squared. So look what I've done in one step. So first off, t formula makes dealing with trig a lot easier because there's no trig, it's just algebra. But with this compound trick, this makes t formula 10 times easier than ordinary trig. Because now, this is just a simple fraction. I just got to collect like terms. The ones cancel. So it's 2t minus 2t squared on top. On the bottom, the t squareds cancel and it's 2 minus 2t. Look how much better that is. So all I've got to do now is cancel anything out by factorizing. So I'll just write it up here, LHS. So here I can take a 2t out. So that's 1 minus t over. And I can take a 2 out of the bottom, 1 minus t. So look what cancels. 2's, 1 minus t's, and I'm left with t. So it's at this stage, once I've cancelled everything out, I look at what I'm trying to prove. Trying to prove it's 10 theta on 2. So when you get your result in terms of just t, you just sub in that t is 10 theta on 2, right, by definition. And that equals the right-hand side. So you can see this is way quicker and easier than using ordinary trig formulas to get this. Right? So you try and use normal double angle formulas for trig. It's not going to be as easy as this, especially with this multiplying one trick for compound fractions. So let's look at one more example. Let's look at this example now. Prove tan 2x plus cot x over tan 2x minus tan x equals cot squared x. So here we can use t formulas because we've got our double angles, x and 2x. But instead of using t equals tan x on 2, we're going to let t equal tan x so that we have the double angle. Which means I can sub in my t formula straight away. 2t over 1 minus t squared plus, now cot x is 1 over tan x. Since tan x is t, that's just 1 over t over. Now what's tan 2x? Well, it's the same as this. And minus tan x, which is just t. So remember, the trick with t formula is you only have to ever use as highest power as 2, right? Quadratics. You should never have powers of 4, only 2's. That means you're using the wrong t substitution. So now we're going to do the same trick by timesing top and bottom by the LCD. So if we look at all the bottoms, we have t and 1 minus t squared. So if your LCD is just their product. So that's t brackets 1 minus t squared. So we times top and bottom. So when we times this fraction here, the 1 minus t squared cancels, but I'm left with a t. So times that with 2t, I get 2t squared plus the t cancels here. So I'm left with 1 times 1 minus t squared. So that's just 1 minus t squared over. So again, the 1 minus t squared cancels. I've got t times 2t, so that's again 2t squared minus, now there's no fraction to cancel, so it's just t times all that. So we get t squared 1 minus t squared. So now we're going to clean up like terms. So here, the t squares are common, so that's just t squared plus 1. Now, on the bottom, I could expand this and simplify, but I always prefer to factorize before expanding because t squared is common. I'll take that out. I'm left with 2 here minus 1 plus t squared, because if I put the minus in here, it changes the sign. So I'll come up to here. So the LHS is t squared plus 1 over t squared brackets 1 plus t squared, and they cancel now, they're the exact same. So that's 1 on t squared. We reduced as much as possible. Look at the answer. Cot squared. Remember, cot was 1 on t. So 1 on t squared is just cot squared x, which is just the right hand side. So you can see, if you know how to use t formula properly, combined with this compound fraction trick, proving these results is much easier than normal trig identities. Okay, so I hope you enjoyed this quick trick on how to use t formula to solve trigonometric identities. If you did, make sure to give us a like. Today we're doing solving trigonometric proofs made easy using the manipulation list, right? Which is a special strategy I invented, right? So let's look today. First off, we're going to go over this special strategy for solving trig proofs, the process. Then we're going to go over a mid-range question for solving trig identities, and if you stick to the end, we're going to go over a hard question for solving trig identities, right? So if you're doing higher level maths, make sure you stick to the end to see that. Alright, so what is this manipulation list and how does it work? Well, 3 simple steps. So first, you're going to pick a side that has more info to manipulate, right? This makes it easy to work with. So we've got the left hand or right hand side, which you'll see in part 2. Alright? So next, we're going to write down the manipulation list on the side of the question. So what's the manipulation list? So it's E, F, A/S, S. E stands for expanding, F stands for factorize, A/S add or subtract fractions, S is simplify or substitute identities, right? So when we're doing proof type questions, these are the 4 basic manipulation tools we have, right? So what we do then is, when we go from one line to the next, we're going to go through this list and pick what can I do, right? That's how simple this is. And the key is we're going to write this on the side, because instead of having to think in your head what can you do, you have it written down. So just note, from going from one step to next, you can always do at least one of these, right? So having this on the side of the question will help you a lot, because you know you have something you can do. Now, the only problem is substitute. You have to know all your identities for trig. If you don't, this process is not going to help, because you're going to get to a step where you have to substitute identity, but if you don't know which identity, then you're going to be stuck for that question. So make sure you know all your trig identities or have them in front of you when you're practicing to make this process really simple. So now let's look at how we apply this list for a mid-range question. Alright, so part 2, let's look at solving a mid-range level question. So we want to prove 1 on 1 plus sine theta plus 1 on 1 minus sine theta equals 2 sec squared theta. So if you're doing, say, year 10, year 11 or a pre-calculus course, this is the kind of question you might see. So what do we do first? Well, we're going to pick the side that has more to work with, or more to manipulate, which is this side. This has way more we can work with than just a single term. So let's write down the left-hand side. Next, let's, in the corner here, separate, so not direct, we don't want to interfere with the work. Let's write our manipulation list. E, F, A/S, and S. So equals, right? So when we're doing proof questions, we work with one side. So what we're going to do now is we're going to go through this list and find the first thing I can do, or the simplest thing I can do. So you ask yourself, can I expand? There's no brackets here to expand, so no. Factorize. No common factors. Add or subtract fractions. Well, what do you know? I've got 2 fractions I can add. So therefore I can do that one straight away. Now I'm going to leave a link at the top here, an info card, to show you a video I did on adding fractions fast. Even though it was with simple fractions, it's the same process here. So if we want to add fractions fast, what we do is we cross multiply, right? So we times numerator 1 with denominator 1. So 1 times that is just 1 minus sine theta, plus 1 times the other denominator, 1 minus, oh that's a plus sine theta. And on the bottom, we just times the denominators together in brackets. Alright, so let's go to the next step. So obviously, whenever you have like terms, that's a part of S, simplify. So simplify your like terms. Okay, so 1 plus 1 is 2, minus sine theta plus sine theta is gone, right? So that's just 2. Now, you can do 2 steps in one here. You don't have to just do that. And then, because let's work with the bottom, right? Now, in this current form, this does look nothing like sec squared theta. So what can we do with this? If we look at the list, straight away expand. I've got brackets and I can expand. But here's another trick. 1 plus sine theta, 1 minus sine theta. You'll notice it's in the form x plus y, x minus y. That's a difference of 2 squares. You learned that in year 9 or maybe earlier. So that's just 1 squared, which is 1, minus sine squared equals. So let's go through the list again. Can I expand anything? No. Factorize. Technically I can factorize that, but that negates this step. Right? So you're not going to factorize. You're not going to negate the previous step you just did. So nothing to factorize. Add or subtract fractions. What's a single fraction? I can't add or anything. So that means straight away I'm left with s. Right? I have to simplify or substitute an identity. There's nothing to simplify, so this is where I have to substitute an identity. There's nothing else I can do here. Right? That's why this list is good, because it rules out everything. So what identity do I use? Well, this is where, as I said earlier, you need your trig knowledge here. So 1 minus sine squared. Well, cos squared plus sine squared theta equals 1. So if you rearrange that identity, this is just cos squared theta. Right, easy. And next line, again, if you go through this, can't expand, nothing to factorize, single fraction, can't add anything. We're left with substitute an identity again. But this is where you look at the answer to help you now. So we're really close. We've got cos single term here, single term in the answer. So you just think, how do you go from cos squared to sec squared? Well, sec theta is 1 on cos theta. So straight away that is just 2 sec squared theta, which equals the right hand side. Okay? So you can see with this list, this question was a lot easier because I knew I had what to do at each step, or I had a menu to pick from, right? It's a lot nicer when we have a menu to pick from. So if you stuck to the end now, let's go to part 3 and look at a hard question. Part 3, so if you stuck here, probably doing some high level maths, right? So let's look at this example. Prove sine 2 theta minus cos 2 theta plus 1 over sine 2 theta plus cos 2 theta minus 1 equals 10 brackets 45 plus theta. So this requires some more advanced trigonometry formulas. So let's start the process. Let's write our list down. But just as a precursor, now trying to go from, you notice these are double angles here, to a compound angle is near impossible. So what I would recommend is, if you ever have a compound as the answer, is to expand the compound, right? So this, if you use a compound formula, is tan 45 plus tan theta over 1 minus tan 45 tan theta, and you remember tan 45 is just 1. So straight away, this is an advanced strategy, which I'll do a video on later, is we can rewrite the question to make it easier to prove. Right, so that's a strategy you have in mind, but I'll do a whole video on that later. Right, so now we want to prove this equals that, because this is that. So that's a lot easier to prove this instead of that. So if we start with the left-hand side, why would we do the left-hand side? Because I'll tell you now, going from theta to 2 theta is a lot harder than 2 theta to theta. Right, because we have double angle formulas that take 2 theta to theta. So what we're going to do is we're going to substitute, well, if we go through the list, can you expand anything? No. Factorize. No common factors. Add or subtract fractions? No, because it's a single fraction. So we're left with substitute identities. And this is where we need to know our knowledge for our double angle formulas. Now sine's easy because there's only one option. 2 sine theta cos theta. Minus 2 cos 2 theta. Now this is an annoying one because cos 2 theta has 3 different options. Right? But the trick with cos 2 theta is to pick the one that makes your life easier. Now notice here we've got plus 1. And cos 2 theta, there's 2 formulas that have a 1. So if I write them on the side here, cos squared minus 1 or 1 minus 2. Right? So 2 formulas introduce a 1. So that means if I pick the right formula, that 1 will disappear. So you think because there's a minus in front, that will change it to a plus 1. So plus 1, nah, that just makes it plus 2. But minus here turns that into minus 1, plus 1 is 0. So straight away, you're going to substitute this formula in because it's going to cancel the 1. So we put it in, it's minus 1 plus 2 sine squared theta plus 1, right? Because the minus changes the sign. And we do the same for the bottom. So sine 2 theta only has one formula. Again, we've got minus 1, right? And a plus here. So we think if we minus 1 here, that's minus 2. But if we minus 1 here, that's gone. So we're using this formula again. So that's a simple trick for dealing with cos 2 theta, know which one you want, and I'll probably do another video on that later if people want that. So now the ones are gone. And what you'll notice is, let's just cancel them out there so I can, because I'm running out of space here. So now let's go through this. Can you expand anything? No. Can you factorize? Yes. Because look at here, I've got 2, it's a common factor, and sine theta. Same on the bottom, 2 and a sine theta. So if I take that out, we're left with this. And what do you notice? These are exactly the same, so they cancel out. So that's great. So this looks a lot better now, right? So to get to the next one, let's go through the list. And always keep an eye on the answer. Can you expand? Well, no, because they're gone, so there's just single terms. Factorize, no. Again, no common factor between these two. Add or subtract fractions, no, it's in a single fraction. So we're left with substitute identity. So the trick here is what identity to use is to look at the answer. I've got cos, sine, and the answer has tan. So you need an identity that relates all those, which is just a very basic identity, tan theta equals sine theta over cos theta, right? So there's a really nice trick we can do to get the answer in one step, right? This is more an advanced trick, right? So if you've stayed this long, you're going to get a nice special trick. So you notice tan theta equals sine theta and cos theta. So that means to get tan theta here, I'd have to divide that by cos theta. And same with that. So what we're going to do is actually divide each term individually by cos theta. Because what happens, what's cos theta divided by cos theta? It's 1, because anything divided by itself is 1. What's sine theta divided by cos theta? It's tan theta, which is what I've just written there. And we get the exact same thing on the bottom, because it's the exact same as the top, but with a minus. And we get the right hand side done. Hey everyone, today I'm going to show you how to do proofs in maths really easily with this special strategy, my last resort method, right? Now warning, you're guaranteed to get 100% in these questions, but make sure you stick to the end to watch out how to do this method properly, right? And why there's precautions, okay? So let's get into what this method is. Alright, so what's this last resort method? Well, it's called doing it in reverse, so that's what name I give it. Right. So it works for questions where you have to prove in maths, algebra, trigonometry, where you have to prove left hand side equals right hand side. So you've got to prove it, show it, or for even for inequalities, right? You've got to show, prove an inequality, greater than, less than, doesn't matter, any variation. So what the method is we're going to assume the actual answer is true and manipulate that answer and work backwards until we get something that we know is 100% true, right? And then here's the kicker, so what you got to do is then you basically rewrite that in the reverse order, and that's how you do the question, right? But warning, this method is probably illegal because you don't like, your teacher won't like you assuming the answer is true. So this is why I call it a last resort method, because I teach this to my students, because if they're stuck in the exam and they're stressing and they need to get those marks, then this is their last resort. It's guaranteed to get for most proof questions. It doesn't work for all proof questions, but works for most of them. And doing it in reverse shows you basically how you would do the question, or one way to do the question normally, right? So what we're going to do is use scrap paper, right? Use scrap paper to do it in reverse, and then in your exam, you're going to write it how you should do it properly, right? So let's look at two examples, one with an inequality, one with a trigonometry proof of how to apply this last result method. Okay, so let's look at this trig proof example. prove cos alpha over 1 plus sine alpha equals sec alpha brackets 1 minus sine alpha. Now last week on Wednesday I did do a video on how to do trig proofs with my special manipulation list, so I'm going to leave a link here so you can check out how to do this properly. Not illegal and really great strategy, but here, let's say you got no idea, let's apply this method, last resort method. So as I said before, if you don't have scrap paper, another way to do this is leave space in and start from the end, right? So let's just say therefore cos alpha on, let's assume we've already proved it. And just go up backwards, assuming it's true. So assuming this is true, what would I do next? Well, I'll get rid of the fraction, times it over, because I noticed I've got 1 minus sine, 1 plus sine. 1 plus sine alpha, 1 minus. And then this is a difference of 2 squares. So that's 1 minus sine squared alpha. So all I've got to know here is one basic identity. But cos squared plus sine squared equals 1. So all I've got to know is this. Cos squared alpha plus sine squared alpha equals 1. Because then that means this is cos squared alpha. So this is cos squared alpha. And now all you need to know is that sec alpha equals 1 on cos alpha. So 1 on cos alpha cancels with that. And look at what we end up with. Cos alpha equals cos alpha. Now you wrote this in the exam, your teacher is going to look at you like you're the weirdest person ever, but this is 100% correct, right? Because look at this, cos alpha equals cos alpha obviously, and all I'm doing is just rewriting it as sec alpha cos squared alpha using this identity. Then I know cos squared alpha is 1 minus sine squared alpha, then I factorize as a difference of 2 squares, and then divide it over and I prove this result, doing it in reverse, right? So you can see how powerful this method is if done correctly. If you write an exam like this, you look mad, but you're still right. You haven't done anything illegal, and you're right. You'll get the marks. Okay. So hope you enjoyed this video. So make sure to give a thumbs up, like, comment. Hey everyone, and welcome to another Wednesday fan favorite video. And today you guys voted for solving harder trig equations using double angle and compound angle identities. All right, let's get started. So to make this video a bit quicker, I'm assuming you know how to solve basic trig equations like this. Okay, so sin x equals half, cos x equals root 3 on 2, tan x equals 1. So when you have a trig ratio equals a number, they're the basic trig equations. So to save time today, I'm just going to reduce equations like this to those, right? Because these are the tricky ones that we're going to have to solve. So I'm assuming you know how to do this. Now, if you want a tutorial on how to solve basic trig equations like this, make sure to comment below. But I'll double the length of the video if I have to go through how to do this. So today we're only focusing on the hard ones. So once I get down to these, I'm done because we can use a calculator to solve for that. So I'm only dealing with how to turn this into that. All right, let's get in the whiteboard. Damn, don't you just love this? Best 5K I spent on this. Alright, so first I'm going to help you, right? So what I'm going to do is we're going to look at this flow chart. Wait, what the, I said flow chart, not grocery list. This thing does malfunction sometimes. Actually that reminds me I do need to shop, so thank you for reminding me, but let's get rid of that flow chart. Okay, there, that's the flow chart. So let's have a look at this flow chart. So when we're solving trig equations, the aim is to reduce it down to sine, cos, or tan equals a number like I had previously. So what we want to do first is bring everything to one side. So then once you do that, you got to ask yourself, can I factorize or use the quadratic formula to reduce it down to sine, cos, or tan equals a number? Because if I can do that, we're done, we can use the calculator. Because most of these you'll be able to factorize or they turn into a quadratic equation you can solve with the quadratic formula. So if you can do that, well, you do it and you're done, right? So if you can factorize or use the quadratic formula, do it, because then you've done. You've reduced it down to a basic trig equation. Well, what if you can't? Well, no. Well, then that means you're going to need to use an appropriate trig identity, which in this case will be your double angle or compound angle, which is what I'm covering in this video. So once you use your appropriate identity, go back to here. Can you now factorize it? Yes, or do it. No, or then you need another identity to help you. So this flowchart pretty much covers most of the types of harder trig identity equations. There are extra hard ones that require special manipulation techniques, but those questions usually will give you a hand to do those. But for most trig equations, following this flowchart, you'll be able to solve it. All right, so let's look at the first example. All right, so we want to solve this trig equation. 3 cos 2 theta plus sine theta equals 1. So everything to one side, let's do that first. Let's bring everything to one side by subtracting this 1. So now you ask yourself, can I factorize that? Or use quadratic formula? Definitely not, because that looks nothing like a quadratic equation. I've got different trig functions, I can't factorize anything. So that means straight away I need to use an appropriate trig identity. In this case, we have a double angle here. So that means I can sub in a double angle for cos 2 theta. So remember, cos has 3 double angles, which makes this a little tricky. But the aim is to reduce it down to a quadratic so that I can factorize it. So if we remember, I did a video yesterday on cos double angle identities in trig proofs. We can use the same logic here. Which identity will make life easier for us? Well, we're going to use this one. The one involving just sine theta. Because in order to get a quadratic equation, we need to only have sine thetas. If I only have sine thetas, then that will be a lot easier to factorize and make life easier. So now I've only got sine thetas, there's no coses left. So now I'll just expand. And I'm just going to bring everything to the other side so that this is a positive. So we get 6 sine squared theta minus sine theta minus 2 equals 0. And what you should notice is this looks like this, where x equals sine theta. So now, after applying the appropriate identity, we can factorize it. So if I do it, I'll just do it here in the corner. So this is two-thirds and a half. So sine theta equals 2/3, or then sine theta equals a half. Now, what I did here was a special technique I have for factorizing. Non-monic quadratics. So if you want to know the special technique I did to get this pretty quickly, make sure to comment below and I'll do a future tutorial on my Tuesday or Thursday tricks to show you how to factorize it this quickly. But we're done for now, because now I've got sine theta equals 2/3, sine theta equals a half. I can just use a calculator now to shift sine and get the value of theta. So that is it for this example. So again, you just follow the flow chart. Bring everything to one side. Can you factorize? No. I need to use appropriate identity. Can you factorize now? Well, yeah. Now, no, I did not have to sub it in like that. I could have just written it down like this. Sine theta minus 4 on 6 sine theta minus 3 on 6 equals 0, and then written it down like that. So when you're a more advanced student, you won't need to actually to sub in x equals sine theta. You'll notice you can just factorize it with using sine theta. All right, let's go to the next example. All right, the next example. So solve for x, tan brackets 45 plus x equals 3 tan brackets 45 minus x. Now if I bring it to one side, to here, we ask ourselves, can I factorize this? Obviously not, because these are not common factors. These are different. These are plus, that's a minus, they're different angles, so I cannot factorize. So I need the appropriate trig identity. Now this is an obvious one because this is a compound angle identity. We got the sum of two angles, the difference of two angles, so there's only one identity we can use, which is the tan 45 plus tan x over 1 minus tan 45 tan x minus 3. So now I'm assuming you know what the compound angle and double angle identities are. So you wouldn't be watching this video if you didn't know the identities. You're just watching because you stuck on how to solve these type of equations, or what tricks you need to look for. So then again, we'll sub the identity in. So now to simplify this, we need exact angles, and you should know tan 45 equals 1. Did make a video, I think it was last week or so, on a trick to remember these exact values using your left hand, but tan 45 is just 1 over 1 minus, yep, just 10x minus 3 brackets 1, yep. Okay. So now we're going to try and factorize this. Now, in order to factorize this, we need to get rid of our fractions. So in equations, in order to get rid of fractions, what we do is we times everything by the lowest common denominator, which would be the product of these two. So essentially, we cross multiply here. So if we do that, what you should notice, if I put this in brackets, that is that times itself. Minus 3, that is times itself. Equals. So now it'd be 0 times each of those, but it's 0 times anything is just 0. Okay, so let me just get rid of the top of the board, and let's continue working up here. So now to expand this, we can use perfect squares. So if you're at this level, you know what a perfect square is. Square the first term, double their product, square the last term, minus 3 in brackets, do the same. All I gotta do now is expand and collect like terms, which I can do in one go. I've got 1 minus 3 times 1, that's minus 2. 2 10x minus 3 times minus 2, that's plus 6, that's plus 8 10x. 10 squared minus 3 times 10 squared, that's minus 2 tan squared x equals 0. So if I put it in standard form of a quadratic, I bring everything to one side, and we'll get this. Because notice, I can just divide everything by 2 to simplify it. So that looks like this. So if I let u equal 10x, that now looks like a quadratic equation. Now can we factorize that? No, but because we know no numbers times to 1 to add -4, so we've got to go to the quadratic formula. That's why I put that in there. You can't factorize the quadratic, you go to the formula. So if I do it here, we get u equals 4 plus or minus 4 squared, 16 minus 4 times 1 times 1, which is 4 over 2 times 1. So if we simplify that further, I'll just do it here. So remember, you've got to simplify surds as much as possible. Root 12 will become 2 root 3, and that just becomes 2 plus or minus root 3. So if I just write the final answer, we're using x, so I should use x. 2 plus root 3, 10x equals 2 minus root 3. So then we can just use the calculator to find those values. And that's pretty much the process you want to go through. Just follow that flow chart. Write that down in your summary book. Right, so last week's video was on how to make maths notes step by step.